Welcome to Techie Wise. In today's video, we will be discussing about Data Encryption Standard. So this Data Encryption Standard is a block cipher symmetric key mechanism. So block cipher, already we know that the message is divided into equal sized blocks and then it is processed. If there are n-bit blocks, then this n-bit plain text will be converted as a n-bit cipher text. And it is a symmetric key mechanism in the sense the sender and the receiver will be using the same key for encryption and decryption process. And data encryption standard is based on Fiestel cipher structure. What is Fiestel cipher structure? That we have already discussed in the previous video. Please do have an insight on that video. We have attached a link for that playlist at the end of this video. Data encryption standard encrypts 64-bit blocks of plain text at a particular point of time. That is, the message is divided into 64-bit blocks and then it is processed. And what about the size of the key? Using 56 bits key. With regard to the user will give a 64-bit plain text block. So the data will be of 64-bit plain text block and the key will also be 64 bits. This 64-bit will be reduced to 56 bits and then it is going to be encrypted. So the strength of the algorithm is dependent on 56 bits. In the sense, if there are 64 bits, how many possible keys will be there? 2 power 64 keys possibilities will be there. So this 64-bit is not going to be used directly. Instead, it is truncated and then only 56 bits is used. So the strength of the algorithm is going to be dependent on 2 to the power of 56. 2 to the power of 56 possible keys are there. So this is the overview, how it is reduced, how 64-bit is reduced to 56 bits. All those things we will discuss now. So now this is the overview of the decryption mechanism. So this 64-bit plain text, as it is based on Fiestel cipher structure, it is going to have multiple rounds and there will be a swap. That is the usual strategy. So this 64-bit plain text comes across the initial permutation. Permutation, as we all know, changing the positions. And then it involves 16 rounds. The number of rounds will be 16 rounds and finally there will be a 32-bit swap. According to Fiestel cipher structure, how it will be processed, the plain text block will be divided into 2 halves and then it is processed. So that same thing holds good here. It is processed and then finally there will be a 32-bit swap and the output of that 32-bit swap will come across a inverse initial permutation and the final thing is going to be the 64-bit output cipher text, and each round will get a unique key. So only 64-bit key is there. This 64-bit should be given as unique key for each and every round. What is the size of, so here you can see what is the size of round key, unique key given for each and every round? 48 bits. So how many keys are required? How many bits are required? 48 bit into 16 rounds. So that many keys are required, but we have only 64 in hand. So we need a key scheduling, that it involves a key scheduling process. This is the key scheduling mechanism. And again, in detail, we can discuss further. So this is just an overview. This 64-bit will come across the permuted choice 1. And output of this permuted choice 1 will be 56 bits. So how it is reduced and what is the order in which the permutation takes place, that we can discuss. Then comes the left circular shift. Then the output is again coming across a permuted choice 2. Then the output will be 48 bits. So here comes 64 bits and here come 48 bits. Then round 1 process. So similar, the repeated in the same similar way, 16 rounds will be processed. Right, and then the final 32-bit swap. So here initial permutation. So we can start key scheduling algorithm, we can discuss later. To start with, we can have a discussion on the key encryption process. So encryption process, you can see the initial permutation. So what is permutation? Changing the positions. So how the positional bits will be 1, 2, 3, 4 like that till 64. right? So this just we are in the initial permutation. This is how the bits positions will get changed. First bit will come to this particular position, and 58th bit will come to this position, and 50th bit of the plain text will come to this position. Like that it goes on. Just have an idea on it. So this is how the initial permutation happens, and this is how the inverse initial permutation, that is after the 32-bit swap there will be a 64-bit, right? So that 64-bit will have the positions from 1 to 3 to 64. So those bits will come across this permutation. So just to have an idea that there will be an initial permutation and inverse initial permutation. This positional values you need not memorize things. Next comes the single round of DES. So yes, it involves 16 rounds, right? So here what happens in each and every round. So this is the single round of DES. So this, what is the input of each round? 64-bit is given as input of each round. As it is based on Fiestel cipher structure, it is divided into two halves, 32 bits and 32 bits. Yeah, this right half comes across the f function. So it comes across the f function, and this f function is not going to be a single step process. Again, it is going to be a combination of substitution and permutation. Already we discussed in Fiestel cipher, it is a SP network, substitution and permutation network. Same thing here. So this 32-bit first passed on through the expansion table. Here you can see the input given here is 32-bit. But what is the output of this expansion table? 48 bits. So this is because the key what we are getting here is going to be a 48 bits, which comes across an XOR operation. So for XOR operation, both the operands should be of same size. So 48 bits. So this 32-bit is expanded. How it is expanded, that we will discuss now. 48 bits, and this 48 bits is going to be XORed. Now the output of this round should be again 64. It should not be increased, right? So this should be reduced to again 32 bits. So here this output of 48 bits comes across a substitution choice. So where we will convert this 48 bits to 32 bits, and this 32 bit comes across a permutation P, just changing the positions. Here we are not going for expansion or contraction, just changing the positions. Now this 32 bit is XORed with the unprocessed right half. This left half is XORed with the, this processed right half is XORed with the unprocessed left half, and this output becomes the right half of the next round, and unprocessed right half comes across the, becomes the left half of the next round, right? Next round. And with regard to the key scheduling, here we can see just an overview. Here the 56 bits is divided into two halves, 28 and 28 bits. And again it comes across a left shift. Each 28 bit comes across a separate left shift. And again, so here you can see this we have 56 bits which should be reduced to 48 bits. That is taken care by this permutation choice 2. So the output of this permitted choice 2 will be 48 bits, right? And after coming across the left shift, so what about the key for the next round, the processing of next round? Again, this unprocessed, that is this after left shift, that output will be given as input to the next round. Okay. Yeah, now we can proceed with the f function. So this right half of 32 bits comes across an expansion table. That's 32-bit should be expanded as 48 bits. So here you can see the 32-bit is placed as 4 bits in each row, right? And each 4-bit is appended with a bit of the previous round, last bit of the previous round, and appended with the first bit of the next round. So for example, here we can see, let us take the bit blocks or A, B, C, D. E, F, G, H, I, J, K, L. So here you can see this block should be expanded as 6. So here you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 4s are 32. I want to expand it to 48 bits. So I need to append 2 bits in each and every block. So it will be 6 into 8 is 48. So each block should be, each 4 bits should be expanded as 6 bits. That is what we are doing here. How it is expanded? Each block is appended with the last bit of the previous block, that is D, and the first bit of the next block. So here you can see, consider this block. So this block is appended with the last bit of the previous block 4 and the first bit of the next block, that is 9. So here you can see 6 bits, right? This is how the expansion takes place in each and every block. And what about this block? Each block should be appended with the last bit of the previous block. So here we don't have any previous block. Here we will consider it as a circular way. So the last bit of the previous block is 32 and first bit of the next block is 5. And similarly here, what is the last bit of the previous block? 28. And what is the first bit of the next block? Circular way. 1. So similarly we can check it out here. A, B, C, D. How we can expand? Last bit of the previous block. So in the sense the previous block is this block. So it is L. And first bit of the next block, that is E. Similarly, what about this one? Last bit of the previous block, that is H. And first bit of the next block, which is A. So this is how 32-bit is expanded to 48 bits. Now we have 48 bits from the key, sub key is there. So we can perform the XOR operation. Now this 48 bits should be reduced to 32 bits. Alright, so here you can see 48 bits till this point we have done, right? So 32-bit expanded, 48 bits XORed with the key. So we have 48 bits in hand. So here, for expansion, for reduction, we use the substitution boxes. So how many substitution boxes are required? So here you can see we have each S box, there will be multiple S boxes. Each S box will take 6 bits as input and it will produce 4 bits as output. So please make a note, we have 48 bits. So this 48 bits should be reduced to 32 bits. So how it is going to be processed? With the help of the substitution boxes. So each S box is going to take 6 unique bits of this 42-bit. So first 6 bits of this 48-bit will be given as input to S box 1 and next 6 bits will be given as input to S box 2. So totally how many S boxes are required? So 48 divided by 6 is 8. So I will have 8 S boxes and output of each S box is going to generate a 4-bit value. So 8 into 4 will be 32-bit. So here the output of this S box. So here you can see the output of the S box 32-bit comes across a permutation. So this is the permutation. So we have the output of the S box that will come across this permutation. So again, you just have an idea that there will be a permutation function, right? Right. Okay, so that will be the 32-bit output. So what is there in this S box? So here we can start with one example. These are the 8 S boxes. Each S box is going to take 6 bits as input, right? So it's going to take 6 bits as input. Let me take A, B, C, D, E, F is the input given to S box 1. Just consider. So here this S box with this input should be used to retrieve an output from this, that is retrieve a value from this table. How to retrieve the value? So here you can see that this S box is having 4 rows and 16 columns. 4 rows and 16 columns. How many bits are required to represent the 4 rows? 2 bits. Right. 0, 0, 0, 1, 1, 0, 1, 1. 2 bits are required to represent the rows. And what about the column? 16 values. So 2 to the power of 4 is 16. So 4 bits are required. So out of this 6 bits, 2 bits will be used to represent the row and 4 bits are used to represent the column. So which 4 bits are used to represent the column and which 2 bits are used to represent the row? So this 2 bits, that is first and the last bit, are used to represent the row, and intermediate middle 4 bits are used to represent the column. Right? Okay. Let us start with an example. Let us take 0, 1, 1, 1, 0, 1. Okay. So this is the input given to S box 1. Just consider. So this 2 bits will be used to represent the row and this 4 bits used to represent the column. So here all we know is 0, 0, 0, 1, 1, 0, 1, 1. Similarly, this is 0, 0, 0, 0, 0, 0, 1. Like that it goes on, and this is 1, 1, 1, 0, 1, 1, 1, 1. Right? So here 0, 1. So 0, 1. So this row. So 0, 1 is this row. And what about the column? This column, right? 1, 1, 1, 0, this column. So what is the value? So this value. So here you can see the output of the S box should be a 4-bit value. So all the entries, all the entries of the S box will be of 4 bits. That is, the value will range from 2 to the power of 16. So here you can see all the values. You can see it ranges from 0 to 15. 0 to 15. So the entries in this S box will be a 4-bit value. So the output will be a 4-bit value. So similarly, from all the S boxes, we have the similar set of entries and we will get a 32-bit output. So this is how the process goes on. So this is how the process goes on in each and every round. So here you can see. So the round 1, 64-bit input divided into 2 halves. Right half comes across an F function and the output of round 1 is given as input to the round 2, the same set of operations. So similarly goes on till the inverse initial permutation. So that's it with the encryption part. So with regard to the decryption, it is going to be in a reverse way. Nothing much different. It is going to be used in a reverse way. That's it. Now comes the key scheduling mechanism. With regard to the key scheduling mechanism, so as discussed earlier, what about the key scheduling we discussed? 64-bit is given as input to the permitted choice 1, which produces a 56-bit output. So there is a contraction as well as permutation, that is reducing 64-bit to 56 bits and then changing the position of those 56 bits. So here you can see just an example of input key. So this is the bit positions of the input key. So here you can see all these 8 bits are truncated in permuted choice 1. So in permuted choice 1, or 8, 16, the bits in 8, 16, 24, 32, 40, 48, 56, 64 will not be there. You can see. Right? So all these bits are removed, thereby the 64-bit is reduced to 56 bits. And then again changing the positions. That's it. Changing the position is with regard to the permuted choice 1. And next comes the left circular shift. As discussed earlier, this 56 bits is not again directly used. Instead, it is going to be divided into two halves, 28 bits and 28 bits. And each 28 bit comes across a left circular shift. Left circular shift in the sense by some set of bits, the bits is going to be shifted, right? So this number of bits shifted is not going to be similar for all the rounds. Here you can see this left circular shift is going to be done in 1 bit. That is, 1 bit left circular shift is done in round 1, 2, 9 and 16. Okay, so for these rounds, the left circular shift is a 1 bit left circular shift, whereas for rest of the rounds, it's going to be a 2 bit left circular shift. So for 1, 2, 9 and 16, it is 1 bit left circular shift. For rest of the rounds, it's going to be a 2 bit left circular shift, right? So here, once the shifting operation is done, then it comes across a permuted choice 2. So this is the permuted choice. Again, this 56 bits. So the output of this left circular shift is going to be 56 bits. Now again, this 56 bits is going to be reduced to 48 bits. So this is how the reduction takes place here, right? So that's it with the key scheduling mechanism. So here you can see with the help of left circular shift, we will get a unique key for each and every round. That's it with the data encryption standard. In the next video, we can have as it deals with 64-bit, it is not possible for us to do with any computational part. So for having a better idea on this, we can have a look into a simplified data encryption standard, which is designed specifically for the educational purpose. Now it is not used for any commercial use. Just for educational purpose, we can have a simplified version, which we can have a look into in the next video. Thank you.